Okay, hey there guys. So for today we are going to study about the introduction to geometry. So this is additional mathematics grade 8. So we have geometry. So for our first lesson we have defined and undefined terms and angle measure. So I'm going to be your teacher. I am Mr. John Manuel B. Padre. So let's start. Okay, so before we tackle the defined and undefined terms in geometry and also define the different angles and measure different angles using different angle measurements and the protractor, first we had to introduce the topic or the concept of geometry and what the word geometry means and where it comes from. So as you can see on the pictures, we have here the different pictures about the earth and different ways to measure it. Okay, and speaking of measurement, geometry comes from two words. So geo, that means earth, and metria, meaning measurement. Two Greek words, geo, earth, metria, measurement. So it's simply the earth's measurements and measurement of earthly objects. Mostly in geometry, we commonly talk about the measurements of the earth. So in Greek times, that was a very big thing for the Greek mathematicians and Greek philosophers. They needed to identify or measure the different parts of the earth and how big the diameter of the earth is and how they would get from place to place. So geometry would help them or aid them throughout that endeavor and also in the future, and also the measurement of earthly objects. So these objects can be in the form of Platonic solids. So Plato proposed that there were 5 essential solid figures. So that was the tetrahedron, the hexahedron, or the cube. Then we have the octahedron and the decahedron, and then the icosahedron. So that's like 4 faces, 6 faces, 8 faces, and 12 faces, and then 20 faces of Platonic solids. So those were the 5 essential Platonic solids according to Plato, the great Greek philosopher and mathematician. So formally defined, geometry is the scientific and systematic study of points, lines, surfaces, solids, and higher dimensional spaces. So for our course, plane geometry and also solid geometry, a bit of solid geometry, we'll study more about points, lines, surfaces, and solid figures. Okay, and so that's the brief introduction for geometry. Okay, so moving forward, we have here the measurements of the earth again, and then we have here Euclid. Okay, so Euclid of Alexandria, okay, was the biggest figure in geometry and in the discovery of geometry. So Euclid of Alexandria wrote a tome, so it's kind of like a very big piece of literature that contains 13 books entitled The Elements. Okay, so the Elements consist of 13 books. Okay, so the books contains theorems, postulates, definitions, common notions. Okay, so those mathematical terms will be defined later, but what you have to know is that the Elements is like the foundation of entire geometry itself. It's kind of like the rule book of geometry, so you can find that there in the Elements. It contains 13 books. It's a mathematical treatise. So the book contains different proofs for plane and solid Euclidean geometry. That's why the reason why we call it Euclidean geometry is because there's also a non-Euclidean geometry that you will study in your in your higher or more advanced maths if ever you try to pursue a mathematics major in your college degree or in your master's degree or doctorate degree. So there you will study more about modern geometry, and that includes non-Euclidean geometries. So those are the geometries for higher dimensional spaces. But for our introduction to the topic and the course plane geometry, we'll only deal with plane and solid Euclidean geometry. And also the Elements contained some proofs and theories about elementary number theory. So number theory is also a branch of mathematics, one of the 4 main branches of mathematics. So to review, there are 4 main branches of mathematics. We have algebra, geometry, calculus, and then number theory. Okay, so number theory deals with the study of numbers. Okay, so not just numbers, they're kind of like discrete numbers, so there's no decimals in those numbers. Okay, so they're more like discrete numbers. Okay, and the elements was kind of like one of those books that tried to find proofs about prime numbers. Okay, because prime numbers were really a big deal way back when, during the Greek times. Okay, so prime numbers were played a very important role, especially those prime numbers, of course, are not divisible. They're not divisible by any numbers or any factor. So those were very important fields of study in mathematics during the Greek times. Okay, so the book, the elements contains 13 books, and the book 1, the first book, contains 23 definitions, 5 postulates, 5 common notions, and 48 propositions. So I will post a link on this video regarding like the online version of the elements, okay, so that you can personally view the first book itself in its online version. So you will see there the 23 definitions that Euclid himself laid out. Okay, so of course it was written in Greek, the language of Euclid, and it was translated in English, or English. It was translated in English. Okay, so 23 definitions, it has 5 postulates, 5 common notions, and 48 propositions. Okay, so I'll give you the link later or in the description below this video. Okay, so the elements, always remember that the elements is the foundation, it's the bedrock of entire geometry and even modern geometry itself. It contains all the proofs, all the starting theorems that we will discuss in this lesson in plane and solid Euclidean geometry throughout the entire year. Okay, so the mathematical terms that were used in the elements. So remember what I said earlier, that the elements by Euclid of Alexandria, is the foundation of geometry itself. So in order to be a good foundation, it has to have solid or sound arguments. Always remember that mathematics uses logic, and in order for these arguments to be logical, they have to follow a specific sequence. Okay, so the sequence, we start off with definitions. Okay, so the definition is kind of like the very basic foundation of these arguments. So it defines what a point is. A point is a figure that has no shape, no width. It's just there's just like a position. That's it. So we define the definitions, try to define the terms that are going to be used throughout geometry, and we're going to see that throughout the next slides. Then we also have axioms. Okay, so axioms are true statements. Okay, and also postulates. Postulates are also true statements, but postulates are more like assumed to be true. Okay, so these are statements that are assumed to be true. And we also have common notions. Okay, these are also true statements, but they are in terms of quantity. Okay, so later I will show you on the description, on the link, about the online version of the elements. Okay, the 5 common notions, and also the quantities that they have, the true statements about those quantities. So these are assumptions that when you hear them, they kind of sound real, but they are really true when you test the validity and the logical soundness of their arguments. And also we have here the proposition. Propositions are either true or not true. So it comes from the word propose. So when you propose something, it's kind of like it's not true, or it can also be true. Okay, so propositions are if and then, if this then that happens. Then we have theorems. So these are the arguments that we are trying to prove. So how do we prove theorems? We use definitions, axioms, postulates, common notions, and also some propositions to prove them. Okay, so we'll discuss more theorems as we go along throughout our lectures. The most famous theorem that you probably encountered is the Pythagorean theorem. A squared plus b squared is equal to c squared by Pythagoras. So those are one of the most common theorems that we have in geometry. Also, we have the corollary. Okay, so a corollary is kind of like a subpart of a theorem. Okay, so we have the theorem, and then it has a subpart, or it's kind of like a part 2 of the theorem, but it's not that major. Okay, and you also have the lemma. Okay, so it's also a theorem, but it's not an important theorem. It's kind of like also like a corollary. Okay, so but a lemma is more like it's a theorem in itself. Okay, a corollary is not a theorem in itself. It follows a theorem. So we have theorem. Okay, so that's 1, and then we have corollary 1.1. Okay, kind of like if it's in an outline format. And there, a lemma is a theorem in itself, but it's not as important as a theorem. Okay, so we'll learn more of these definitions, and we'll also see some examples of these definitions as we go throughout our lectures here in Introduction to Plane Geometry, and also a bit of solid geometry. Okay, so the first, we have 3 undefined terms. Okay, so we have 3 undefined terms. We have the point, the line, and the plane. So what you're seeing right now on the screen is a circle, and in the circle there's a point there at the center labeled point A. So the point is the first undefined term by Euclid. Point is an undefined term in geometry that has no size, no dimension, merely position. Okay, so a common example of a point is when you graph a point on a coordinate plane. Okay, so you find its x value and its y value, and then you plot it. Okay, so there's only position, but that point has no size. It has no definite size. It has no definite dimension. Okay, so point, this is the most basic definition that we have. And to clarify defined and undefined terms, the geometers, the mathematicians back then, they have these two terms, undefined and undefined terms. So for undefined terms, these are the types of terms that they don't have a common agreement with of how to define them. So Euclid has a definite definition about it, but point also may have another definition in some countries or in some mathematicians' books. That can also be true. So that's why it's also called an undefined term, because the definition of a point in geometry is very universal. Okay, so even if it's universal, there's kind of like still variations of the definition. Okay, but despite of those variations, they all point to a single meaning. Okay, so that's the point right there. This is the first undefined term. And of course, the defined terms are the types of geometry terms or types of mathematical terms that stem or come from the undefined terms in geometry. Okay, so then we have here a figure. So you're seeing a line. So we call that line CD. Okay, and we can also call it line M, the lowercase letter m. So line is also one of the undefined terms. It is the second undefined term. Okay, so it consists of infinitely many points that extend without it on both directions. Okay, so it has the arrow signs there, so it goes east to west, north to south, or any kind of direction. So it contains infinitely many points. That's the best definition there. But other mathematicians, other geometers, other people who study and written mathematical texts and scholarly texts about geometry may have a different definition for a line, but still the meaning still goes towards this definition right here. It consists infinitely many points that extend without and on both directions. Then we have a line is usually named by using a lowercase letter, like you see here on the example, letter M. Okay, or any of the 2 points on the line. So we can also call the line CD. Okay, it's kind of like CD, and then there's a what do you call this? A script of a drawing of a line. So 2 points are said to be collinear if and only if the 2 points are on the same line. So we can say that point C and point D are what? They're called collinear because they lie on the same line. So some of these definitions might sound like pretty obvious to you. Like, of course they're collinear. You find them in the same line. But the importance of of acknowledging of laying out these terms in the first part of the elements of Euclid's elements in geometry is very, very crucial, because you may have multiple definitions of a line. Okay, so you may have multiple definitions of collinear points. So it's very important that Euclid laid out the foundation really well. Okay, so you might say that, oh, that sounds so factual. Okay, so 2 points on a line, they're collinear. Of course they're collinear. What else would you call them? Okay, so the reason why they sound so factual is because Euclid made sure that they sound that way. Euclid made sure, and all of the mathematicians who edited the elements throughout time made sure that way it sounds factual, because the elements is based on facts. Okay then, so we're finished with our second undefined term, which is a line. Now we move forward with our third undefined term, which is a plane. So as you can see on the figure here, we have here kind of like a shape of a rhombus. Okay, so there's kind of like a rhombus shape there, but that is actually a plane. Okay, so we call that plane Q. Okay, so let's formally define an undefined term, which is a plane. Okay, so what is a plane? So a plane is the third undefined term. It can be illustrated as a flat surface with no thickness, and that extends without end in all directions. Okay, so for practicality purposes and for visualization purposes, what we did here is we kind of like enclosed the plane into a rhombus. Okay, but the formal definition of a plane is it can extend without end, meaning there can be no boundaries. It also means that it extends in all directions, so there could be no boundaries in this figure. Okay, so there's no thickness. Okay, there's no specific thickness, but it extends in all directions. So we named that plane as plane Q, or we can also name it as plane EFG. Okay, although the plane has no boundaries, it is usually pictured using a four-sided figure, like this one, like a rhombus or a square. Planes are named by a capital letter, or plane Q, or 3 points on the plane that are not on the same line, like plane EFG. And points are coplanar if and only if they lie on the same plane. So that means since points EFG line on the same plane, we can therefore say that points EFG are coplanar points. Okay, so that's all. Okay, so we move forward with defined terms. Okay, going back, we have 3 undefined terms. So what are they? That's the point. The first one is the point. It has no thickness, no specific shape, just a position. Then we have the line, infinitely many points that extend in both directions. Okay, and then we have the plane. Okay, so plane it has no thickness, but it extends in all directions. Okay, so now that we have the 3 undefined terms, let's move forward with the defined terms. So the first defined term in geometry is the segment. Okay, so a segment is a set of points on a line if and only if it contains 2 points called endpoints and all the points in between them or between them. Okay, so we have here line Q, and then we have 2 points, point R and then point S, and then the segment there is segment RS. Okay, so and all of the points within segment RS is of course part of segment RS. Okay, so they kind of like sound factual. Okay, but nevertheless they are very much essential, okay, for our definitions. Okay, then we have, okay, so after segments we have now the ray. Okay, so this is the second defined term. Okay, so what is a ray? Okay, so ray is a set of points on a line that has fixed point. It has a fixed point on the line but no endpoint. Okay, so we only have here one fixed point on line Q. Okay, so we see their line Q, and we have their 3 points, point R, point S, and then point T. Okay, so on line Q we have here point R. Okay, so that's the endpoint, but point R goes on infinitely on the right direction. Okay, so it goes on infinitely. So that's what you call array. Okay, so a line has it goes infinitely on both directions. Array goes infinitely only on one direction. So there. So it can stand infinitely only in one direction. It can pass more than one point when it is extended infinitely. Okay, after having defined the most common definitions that we're going to find in geometry, so we have three undefined terms again. Those are the point, the plane, and the line. And then we have two defined terms. We have the segment and the ray. So after having introduced to the formal definitions of those geometric terms, we now move forward with angles. Okay, so what is an angle? Angles are, of course, used in our daily lives without our knowledge that we're already using it. Okay, so let's have some application. So where do you commonly use angles? So a surveyor may use angles on measuring a certain piece of land and then finding the angle of elevation or depression of that specific land, okay, or where the surveyor plans, or where the client of the surveyor plans to build a specific house or a specific property. Then we have here a physicist. Okay, physicists always use angles in terms of rotating bodies. Okay, so when they launch rockets into space, they use angles. They use their knowledge about angles, and mostly those are computer simulated. Okay, so with the help of computers made by mankind, and also with the help of angles, we are able to track at which speeds those rockets go into space. Okay, so that's very important in science. And also in sports, angles are used sometimes without even the sports player or the player knowing that they're using an angle. For example, in tennis. Okay, so in tennis, we have here, I think that's Serena Williams. Okay, so Serena Williams plays tennis without her knowledge, or sometimes with her knowledge of an angle where to serve the tennis ball at a specific point. Okay, so a tennis player uses his or her knowledge about angles in order to find an advantage, in order to win and to serve the best offense in the first part of the tennis match or tournament. Okay, so what's the formal definition of an angle? Angles formally defined is any figure if and only if it is the union of two non-collinear rays, the sides, and having a common endpoint, the vertex. Okay, so let's highlight here two parts. We have two non-collinear rays. So what does that mean? Non-collinear, meaning they do not lie on the same line. So these rays are either going opposite ways, or sometimes not opposite ways. They're kind of like just opening, but they don't lie on the same line. So non-collinear. So two non-collinear rays. And of course, since a ray has an endpoint, those two non-collinear rays have a common endpoint, and we call that the vertex. So that's an example of an angle. So we can name that angle ABC, angle CBA, or angle B. Okay, so surveyors and navigators have sophisticated tools in measuring angles. So they kind of have like sextants or digital devices to measure different types of angles, GPS systems. Okay, but for students, of course, and also for starting for students in geometry, the most commonly used tool in measurement of angles is of course the protractor. Okay, so this is an example of a protractor. Okay, we commonly see a protractor. Most likely you have seen a protractor. Okay, so this is the parts of a protractor. Okay, most likely you have used it in your 4th grade period or 5th grade when you were studying about angles. Okay, So a protractor, just to review, has like 180-degree measurement from 0 to 180, and it has 4 parts actually. So we have here the center point. That's where we put the common point or the vertex of the angle in order to find its measurement. Then we have the zero edge line. Okay, so that's the line that the angle or the ray of a specific angle has to follow. Then we have the inner scale. So the inner scale measures from 0 to 180, and also the outer scale 0 to 180 degrees. Okay, so this is measured in degrees. And then in the inner scale, it's used to kind of like guide. Okay, it's a guide for us to measure the specific measurement found on the outer scale. Okay, so sometimes we call those measurements, the specific measurements, we call those crosshairs. Okay, so the crosshairs of the measurements of those different degree angles can also be measured on the outer scale. Okay, so measuring angles using a protractor. Okay, let's say for example we have this figure and we have here 1, 2, 3, 4, 5, 6, 7. Okay, let's say for example 7 angles, but we can make more angles using this figure. Okay, so there are 3 types of angle measurements. Okay, and we're going to use this illustration to name the 3 types of angle measurements. Most likely you are familiar with them. Okay, so you've already discussed it in your elementary days or in your elementary years, but let's try the review. Okay, so an acute angle is any angle if and only if its measurement or the measurement of angle x. Okay, so it's an arbitrary angle. So measurement of angle x is from 0 to 90 degrees. And we have here the measure of angle BAC is equals to 32 degrees. So if you look back to the protractor, angle BAC measures 32 degrees if you start from the inner circle. From the inner circle. So the estimate is like 32 degrees. And then also angle BAD. Angle BAD measures 52 degrees. So BAD measures 52 degrees. Then we also have a right angle. Okay, so this is the most commonly known angle. It's any angle that's measured if and only if the measurement of angle x, the arbitrary angle, is 90 degrees. Okay, so we have here, if you're going back to the figure, angle EAB and also angle EAH measure 90 degrees. Okay, and then we have the obtuse angle. Is any angle if and only if its measurement is between 90 degrees and 180 degrees. So we have there angle BAF and angle BAG. So let's go back to the figure. So we have your angle BAF, it measures 120 degrees, and angle BAG, which measures, if you look at it closely, it kind of like measures 148 degrees. Okay, so those are our angles. Okay, so those are 3 major types of angle, and we also have a special angle. So this special angle is called a straight angle. Okay, so a straight angle measures 180 degrees, and there's only one angle that measures there 180 degrees on the figure. It's angle BAH or angle HAB. Okay, so there, those are 3 types, and we have 1 special type of angle. Okay, so that's the measurement of a straight angle, angle BAH or angle HAB, that measures 180 degrees. Okay, now, so we've identified the introduction to geometry. We've been introduced to the origins of the word geometry, and also we've identified the defined terms and the undefined terms in geometry, some of the major defined and undefined terms, and also we have a formal grasp of what an angle is. We're going to introduce the first postulate, okay, that we're going to use in geometry, and throughout all of our topics in geometry we're going to use this postulate. It's one of the most basic. It's called the angle addition postulate. Okay, so let's say we have this figure here. Okay, so the angle addition postulate mainly says that if you're given this big angle, angle GEM, okay, so we can find the measurement of angle GEO and angle OEM if we add them together. That's just what it simply means. So the measurement of a specific angle, a big angle that contains two smaller angles, if you add the measurements of those two smaller angles, then you'll get the measurement of the big angle. Okay, so it sounds factual again, but again, that's the primary definitions or primary foundations or the bedrock of geometry. Okay, so to formally state the definition of the angle addition postulate, okay, so this is what it says. The angle addition postulate is the measure of an angle formed by two angles side by side is the sum of the measures of the two angles. So that's what it says. The measure of an angle formed by two angles side by side, like we've seen on the figure a while ago, is the sum of the measures of the two angles. Okay, so we're going to continue with our problem. So given that we have the measurement of angle GEM is equal to 82 degrees, find the measurement of angle GEO and angle OEM. Okay, so but we also have here the measurement of angle GEO and angle OEM in algebraic expressions. Okay, so the measurement of angle GEO is 3x minus 8 degrees, quantity 3x minus 8 degrees, and for measurement of angle OEM we have the negative 2x plus 76 degrees. Okay, so we have those two measurements for those two smaller angles. So how do we solve the measurement of angle of those two angles? Okay, so we do that by simply using the angle addition postulate. Okay, so it's stated by the angle addition postulate that the sum of these two angles, angle GEO and angle OEM, should equal the measurement of angle GEM, and that's already given. It's 82 degrees. Okay, so we can find that. So that's measurement of angle GEO. Okay, so let's write that neatly. Plus the measurement of angle OEM is equal to, so what's the measurement of angle GEM? That's simply 82 degrees. But we're just going to write the formula here so that it can be stated formally, and that so that we can follow the specific procedures. Okay, so we have here the measurement of angle GEM, that's 82 degrees, so we can write that here, 82. Okay, and then we have the measurement of angle GEO, so that's 3x minus 8. So just right there, 3x minus 8. Okay, in order for us not to be confused, we can write here parentheses, and then plus the measurement of angle OEM. So what's the measurement of angle OEM we have there? Negative 2x plus 76. Okay, so we're just going to do some algebra. Okay, simple algebra in order to solve this. Okay, so we have to put our constants on the right side and our variables here on the left side. So 3x minus 2x so 3x minus 2x is equal to 82. Okay, 82. So that's negative 8. When you transfer that, that's going to be positive 8 plus 8, and then that's plus 76. Okay, plus 76. When we transfer that to the other side, it's going to be minus 76. Okay, so moving forward, we have here 3x minus 2x, so that's simply x. Okay, and then is equal to 82 plus 8, so that's like 90 minus 76, that's 14. Okay, so the value of our x is 14. Okay, so you don't need to write degrees. Okay, so the value of x is 14, and we simply substitute that value there, okay, on our givens here. Okay, so the measurement of angle. Okay, the measurement of angle, I'm sorry for that writing. GEO is equal to 3x minus 8, right? Okay, 3x is equals to 3x minus 8. Okay, so we simply substitute 14 there. So, okay, so 3. Okay, so 3 times 14 minus 8. Okay, so what's 3 times 14? Okay, so that's simply 42. Okay, 42. Okay, 42 minus 8. Okay, so that's kind of like 34, right? Okay, so that means the measurement of angle GEO, okay, is 34 degrees. How about for the measurement of angle OEM? Okay, so the measurement of angle OEM is negative 2x, negative 2x plus 76. And also the same process, what we have to do is we have to substitute the value of x there for negative 2x. So that's negative 2 times 14 plus 76. Okay, times 14 plus 76. And what's negative 2 times 14? That's simply negative 28. Okay, negative 28 plus 76, you get okay, so you get 48 degrees. Okay, so the measurement of angle GEO is 34 degrees and the measurement of angle OEM is 48 degrees. So we have our answers, but are we sure that they're right? So how can we check? So we have to use the same formula that we have here, measurement of angle GEO plus the measurement of angle OEM is equals to the measurement of angle GEM. Okay, so we can simply substitute what we have solved. Okay, so we have the measurement of angle GEO, so that's 34 degrees, plus the measurement of angle OEM, which is 48 degrees. Okay. 48 degrees is equals to measurement of angle GEM. So that's given. That's 82 degrees. Okay, and when you add 34 degrees and 48 degrees, what do you get? You get 82 degrees. Okay, and that proves our answer that we have the correct values for the measurement of angle GEO and the measurement of angle OEM. Okay, so we simply use the angle addition postulate to get that. And therefore, the measurement of angle GEO, again, is equals to 34 degrees. And the measurement of angle OEM is equals to 48 degrees. Okay? And we all proved that using the angle addition postulate itself. Okay, so that's it for today. Okay, so thank you for watching and listening. Again, the link for the online version of the elements is posted below, so you can check that so that you can check like the cool definitions and the formality of geometry itself, and how and also appreciate the beauty, the simple beauty of mathematics and geometry itself. Okay, so that's it for today. Thank you for listening and have a good one. Bye bye for now.